The standard for this video is graphing polynomial functions. Our objectives include determining the degree of a polynomial function, determining the end behavior of the graph of a polynomial using the leading term test, identifying factor zeros and their multiplicities, and then graphing a polynomial function using zeros, multiplicities, and end behavior. So we'll do all the pieces and then we'll put it together to make a graph. You'll see a lot of the factoring, zero product property, synthetic, all that good stuff. So recall here, we start for determining the degree. A polynomial function p is given by p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down to that a sub 1 x linear term and that plus a sub 0 constant term at the end, where the coefficients a sub n minus 1, all the way down to a sub 1 and a sub 0 are real numbers and the exponents are whole numbers. The polynomial has degree n and leading term a sub n x to the n. So for one, we're just going to throw out some examples. We're going to identify the leading term and degree of the following polynomial functions. We start with a constant function. We can just give an example. Instead of doing like y equals c, we can just say like y equals 4. If you want to think of it as having a degree, it'd be a 4x to the 0 term, because we know x to the 0 is equal to 1. Right, so that wouldn't affect the value there at all, but we can get the degree from it, right? That a sub n x to the n, our n here would be 0, so a constant has degree 0. Its leading term is the only term, that 4, and the leading coefficient is the 4 as well. We can expand on that a little more here. With the linear, I'll go with something like 2x minus 6. Doesn't matter what we put there, just that mx plus b form we learned for linear functions. For this one, we would have degree 1. Our leading term is the 2x, and the leading coefficient is just that 2 in front. For quadratic, we want a power 2, so y equals, let's go, minus 1/2 x squared. We can have all the terms going down. We can miss some terms like we had for like polynomial division and that, but I'll keep them all here for a sec. So plus 3x minus 4. Right, we can go all the way down to that constant term or that power 0 term. Our degree here is that leading 2, right, our leading exponent. Our leading term is the minus 1/2 x squared, and the leading coefficient is just that number in front, the negative 1/2. Right, that would be our a sub 2. For our cubic, we want to go up to power 3. Just to fit everything, we can show we don't need all those other terms, but how about a minus 3x cubed? We could even stop there. We'll put a minus 7 here just for funsies. Our degree, 3, right, that leading power. The minus 3x cubed is our leading term, and the minus 3 our leading coefficient. We can go quartic, again just for fun, but we're looking at something x to the 4th. We can do plus 2x squared minus 3 or something. And our degree would be 4, right? That highest power we have. Our leading term is the x to the 4th, and just to show it once, the coefficient in front of there would be just a 1. All right, note here, if a polynomial is in factored form, we use exponent rules to determine the degree. So if it's in that nice descending order, highest power to lowest, that highest power, or that a sub n x to the n, that n gives us our degree. If not, we can use our exponent rules. So here's our factored form for a couple in 2. For a, we have f of x equals x minus 3 times our quantity x plus 4 squared, and we want to determine the degree of these polynomials. So if a power isn't written, or that exponent isn't written, we know it's a 1. Since we are multiplying these together, we can add to get our degree, right? Multiplying with the bases, we add the exponents. That's a very simplified version of saying it if we did multiply these out, just to see one. And then hopefully you'll trust me. X minus 3 is just x minus 3, x plus 4 squared. We've got to do that binomial expansion, so the x squared plus 8x plus 16. Right, you could do x plus 4 times x plus 4 on the side. And then if we did, so here this is still, let's call it f of x instead of just an example. If we did multiply it out, we'd get this, which would become x to the 3rd with the x times x squared. We can get an 8x squared, a minus 3x squared, a 16x, a minus 24x, and a minus 48 when we do all our distribution. And we don't really care about any of these lower terms when we're talking about degree. All we care is that that first term is going to be an x cubed. So it's not that we're multiplying the same base and adding the exponents, but it's that if we multiplied this whole thing out, those leading terms, those x's in each of our binomials, would get multiplied together to make our highest power. So we just have an x to the first here and an x squared over here, even though there'd be some more stuff that comes after. All right, for b, we have x to the first times x squared plus 4 cubed times x minus 3 squared. And again, to kind of simplify the process, it's an x to the first. If we did expand this cubic, we'd end up with an x to the sixth, right? That's our 2 times 3 plus some more terms. And then we'd end up with an x squared. We know it's minus 6x plus 9, but just some other stuff. And so it's that x to the first plus the 6 plus the 2 to give us our degree here of 9. If you want to do it right from the beginning, we've got to think we have that 1 getting multiplied by, so adding our exponents, that 2, but the 2 is raised to the third power, so 2 and 3 would get multiplied together by our exponent rules. And then we're adding on that 2 that we're multiplying by at the end. So we get a 9 there, right? Either way we want to look at it. If you did have to multiply it all the way out, you could. You'd end up with an x to the 9th plus and minus a bunch of other terms. But we only care about that leading term for the degree. All right, we move on to determining the end behavior of the graph of a polynomial using the leading term test. We have a note here, the end behavior. Of a polynomial function is what happens to the function value and thus to the graph as x approaches infinity or as x approaches minus infinity. So all polynomial functions of even degree will have the same end behavior as the, we can say, squaring functions or squared functions. And so that's that y equals x squared from our toolkit functions, that parabola that opens up. And so we can say a couple other things with that. We can use that limit notation that we've seen a couple times now to say the limit as x approaches infinity. So as we go all the way out to the right on our number line, the limit of our function is also infinity. And the limit as x approaches negative infinity of f of x, we'll say is infinity for this one. So that's the original. We can draw a picture to go with it. So our end on the left as we go out towards negative infinity is up towards positive infinity. We don't know what's happening in the middle, so we'll squiggle here. And we'll go up as we go out towards positive infinity, up to infinity as well. So this happens if our leading coefficient, that a sub n, is greater than 0. Just like if we have the positive x squared, it opens up. Right, both ends go the same direction. If, we can use some blue here, if a sub n is less than 0, just like minus x squared would flip over, we see the same thing happen here. We can say the limit as x approaches, we can start with the same infinity of f of x here, would go down towards negative infinity. And likewise, our limit as x goes to minus infinity of f of x would be minus infinity. So on the left, we start from the bottom. We do some stuff in the middle that we're going to figure out as we keep moving through the notes, and then we end up going back down towards infinity, or negative infinity, sorry, as we move out to infinity. So as we go to the left towards negative infinity, we're going down towards negative infinity, and as we move out to the right towards infinity, that graph's running down towards negative infinity. And again, just think back to the reflections we did for transformations for y equals x squared. If it was positive, we open up. The same is true for every even degree polynomial. If there's a negative in front, that's reflecting us over the x-axis, so both ends are going down. And so you can probably think of what's coming next for the polynomial functions of odd degree. They're all going to have the same end behavior as the cubic functions. So that's our y equals x cubed. We know for that one we'd start down and come up as we move to the right. So we can say for that one, and here maybe I'll organize it better by putting the a sub n out to the left first. So if our a sub n is greater than 0, if we have a positive leading term, our limit as x approaches infinity for our function f of x would be infinity, and our limit as x approaches negative infinity for our function is negative infinity. And so we can see or represent it again just looking like that x cubed off on the left, except for higher degrees. We don't really know what's happening in the middle. So we're coming up from the bottom, we'll wiggle around, and then we'll keep going up towards the top. So as we go out x towards infinity, we go up to positive infinity. And as we're moving or looking to the left towards negative infinity, our graph's going down to negative infinity. So we can match those limits with what we can see on the graph. Last one here, we can do if a sub n is less than 0. So we're going to see that same reflection over the x-axis we saw with x cubed. And now our limit as x approaches infinity for our function f of x would go down to negative infinity. And our limit as x approaches negative infinity for f of x would be up to positive infinity. So we're going to see that graph just flipped over. As we go out towards this negative infinity, we'd be up towards positive infinity. We'll do some stuff in the middle, and then as we go out towards infinity, the graph's going to go down towards negative infinity. Right, so again, hopefully connecting those limits to the pictures, but really it's our positive x cubed, starts on the bottom left, goes off graph top right if we have a positive leading coefficient, and it reflects over the x-axis, so it comes from the top left and ends off the bottom right for any odd degreed polynomial. So we want to determine degree, leading term, and end behavior for the following functions. For f of x, we can see that leading term is a minus x to the fourth, which gives us the two things we need to determine the rest. Our degree is 4, and our leading coefficient is minus 1, so less than 0 for a degree 4 gives us, we can draw the picture first, that's maybe easier, and then attach the limits to it. So since it's a negative even, both ends are going in the same direction, and the negative makes both go down with that reflection. So we can say our limit as x approaches negative infinity for our function f of x is negative infinity. And our limit as x approaches positive infinity for our function f of x is also negative infinity. For b, we've got that degree or multiplicity we'll talk about a little bit again below, but power 1 there for the 2x minus 3 factor, and then the 3x plus 4 squared. If we think again, just our small multiplication, instead of multiplying the whole thing out, just what happens with that first term, we'll have a 2x times a 3x squared, right? If we square that binomial, let's show it again once, and then hopefully we can trust. We'll get this 2x minus 3. If we square that binomial, we get the 9x squared plus 24x plus 16. And then if we kept multiplying that out, we'd get an 18x cubed plus some other stuff. All right, so again, we only care about that leading coefficient. Those are the values we took for this leading term over here. The 2x is still 2x. The 3x squared would give us a 9x squared. And if we do multiply those out, we get that same leading term of 18x cubed. So that gives us a degree of 3 and leading coefficient of 18, which is greater than 0. That's the important part over here, right? Negative 1 was less than 0. So for that cubic, we can draw the picture again first. We're going to start bottom left, run off the top right, and we can connect it to our limits. Our limit as x goes to negative infinity of f of x. As we're working left on the graph, or looking left, we're going down towards negative infinity. And our limit as x approaches positive infinity of f of x is going to go up and off towards infinity. For c, we've got h of x. I just said it, I read h of x, so these should all be g's over here, right? We've got different names for these functions, so we don't confuse them. So our limit's there for g of x for b. For c again, then we have h of x equals minus 2x to the fifth minus 3x cubed plus 2. We can see that leading term already in descending order here, so the minus 2x to the fifth gives us our degree of 5 and our leading coefficient of -2, which is less than 0. So we have an odd degree with a negative leading coefficient, so we're going to reflect what we had for B. Start in that top left, do some stuff, and then go off in the bottom right. We can connect to our limits. As x goes to -infinity for our function h of x, our limit would be infinity, right? As we look left, our graph goes up forever. And our limit as x approaches positive infinity, so as we look to the right, our graph's going down towards -infinity. For D, we have that leading term, again, already in our descending order, so just x to the 6th, we take the first one. It's got a degree of 6 and a leading coefficient of 1, which is greater than 0. So an even degree with a positive leading coefficient, both ends are going to go up. So we can draw our picture, connect it to the limits again. Our limit as x approaches -infinity, so as we look to the left for our function k of x is infinity. And our limit as x approaches positive infinity for our function k of x also goes up towards positive infinity. So limits are good. Happy if you can draw the picture because that's what we're going to need for the graph. So just connect that again. Even degree looks like x squared if it's got a positive leading coefficient, minus x squared if it's negative. For the odd degrees, looks like x cubed if we've got a positive leading coefficient, and minus x cubed if we've got a negative. All right, to fill in those squiggles in the middle, we've got to identify factors or zeros and their multiplicities. So a couple of recalls. Every polynomial function of degree n with n greater than or equal to 1 has exactly n zeros, counting multiplicities. So when we solve those polynomial equations for a degree 4 polynomial, we found 4 zeros. For degree 3, we found 3. For degree 5, we found 5. Sometimes we had those repeated zeros, so like we saw above or like we'll see below. Like x minus 1 squared there for 4a is a repeated zero, repeated factor, so a repeated zero. But we'll fill in definitions in a sec. Recall here, if x minus c is a factor, then c is a zero of the polynomial. And a definition. The number of times a factor appears in the factored form of the equation of a polynomial is called its multiplicity. And really, we just want to think back to the toolkit functions and the x squared, x cubed for these again. The multiplicity of each linear factor gives us more information about the graph near the zero. So we'll talk about end behavior, which is off towards the infinities, towards the ends of the graph. And we'll talk about behavior near a zero, which is what happens at each of these intercepts or roots. So if the degree or multiplicity of a factor is even, the graph will, we can say touch, or you'll see bounce sometimes off the x-axis. And if the degree or multiplicity of a factor is odd, the graph will cross. That's for, we can say degree 1 or multiplicity 1, or we're going to go with wiggle, and that's for degree 3 or more, right? Or wiggle across the x-axis. So think about the difference between, if I can fit some scribbles, let's go on the left here for cross, about what happens with like a linear function. It just goes straight through, so like y equals x, versus what we drew above for y equals x cubed, where we kind of come up and wiggle through that zero. So that's our difference. We'll flatten out more around the zero with the higher degrees. And for the touch or bounce, again, we're thinking about y equals x squared. So that was a cross. This is our wiggle. And this would be our, I usually call it a touch, but you'll see bounce if you look it up sometimes too. But we just touch the x-axis and then bounce off. So we're going up again. Okay, so for 4, we're going to determine the zeros of the polynomial, their multiplicity, and the behavior of the graph near each zero. So really, we just want 3 lines. We're going to do our zeros, we're going to do their multiplicities, and then we're going to do their behaviors. So zeros come from just us solving the zero product property. We really just want to set each of these equal to 0. We can factor fully if it's not fully factored, or factor completely, especially if it's just in descending order, we'll have to do the factoring. But our zeros here, we can see If x minus 1 squared was equal to 0, we'd have to sub in 1 to get a 0 there. For x plus 2, we'd get negative 2. Our multiplicity comes from the degree of each, or how many times it's repeated. So we have a multiplicity of 2 here, and a multiplicity of 1 for the negative 2. Which means when we get close to negative 1, we are going to, you can put a T for touch, or B for bounce there for the behavior. And since we have degree 1 for that minus 2, or multiplicity 1, the graph's just going to cross there. So I can write it out the first time. We can write out touch and cross. You can just use T and C. W for wiggle we'll do in a sec. For B, we've got f of x equals x squared times x minus 2 times quantity x plus 3 cubed. Our zeros, their multiplicities, and the behavior near each. So our first 0 is 0, right, for that factor x. For x minus 2, we'd have 2 as a 0. And for x plus 3, we'd have negative 3 as a 0. There are kind of two schools of thought here. Either put the zeros in the order you'd see them on the x-axis, or just take them in the order you see them in the function. You can see maybe that I like to do it in the order I see them in the function. That keeps more students from messing up the multiplicities. If you start putting the zeros out of order, then oftentimes you'll confuse where the multiplicity goes. And usually when you're looking at the actual graph, you're going to place minus 3 where minus 3 goes, 0 where 0 goes, 2 where 2 goes. So I think less mistakes doing it this way, but you're welcome to order them from left to right as well. We can see our multiplicities again, right? That exponent or degree for each term. So we have multiplicity 2 for 0, 1 for 2, and 3 for negative 3, which means we are going to touch the x-axis or bounce off. We're going to cross at 2, and we're going to wiggle across at negative 3. For C, we have f of x equals 2x cubed times quantity x squared minus 4 times x minus 1. So threw one in there just so we can talk about we need to be factored completely. We need to have those linear factors. This is a difference of squares, so it'll factor into an x plus 2 times an x minus 2. We still have that 2x cubed out front, and then the x minus 1 at the end. Now we can get our zeros, their multiplicities, and the behavior near the x-axis for each. For our zeros, 2x cubed or x cubed is going to give us 0 of 0. For x plus 2, we get a negative 2. X minus 2, we get a positive 2. And for x minus 1, we get a 1 for our zeros. For the multiplicities, that x is cubed, so multiplicity 3. The x plus 2, x minus 2, and x minus 1 all have multiplicity 1s. They're not repeated at all. So we're going to wiggle across at 0, and then we'll cross at negative 2, 2, and 1. Right, so just straight across like y equals x. For D, we have f of x equals minus quantity 3x minus 1 times our quantity x plus 2 squared. If you need to do some extra work, set it equal to 0, set each equal to 0, you can still, but most of you are good with those two steps. Usually, so our 0 for the first one is 1/3, right? For that first factor, add the 1, divide by 3, and then we get negative 2. For the 1/3, we've got multiplicity 1. For the x plus 2, or negative 2, 0, we have multiplicity 2. So we're going to cross and then touch the x-axis. All right, let's put some of it together. So we're going to graph polynomial functions using zeros, multiplicities, and behavior. Note the graph of a polynomial is smooth and continuous. Smooth means that it has no sharp points. Think like absolute value. And continuous means you can draw it without picking up your pencil, like we've talked about. For 5, then, we want to graph h of x equals x plus 1 times our quantity x minus 2 squared times x minus 4. For step 1, we want to determine the degree and end behavior of the function. So that first factor is just repeated once, and same with the last factor since there's no exponent given. So again, we're kind of simplifying things for these degrees, but my first x is just to the first. I'm multiplying it by an x squared, so I'm going to add 2 to my degree, and then multiplying it by another x to the first, so I'd add a 1. That's going to give me degree 4. Really, my leading term, since there's nothing in front of any of those x's, if I multiply them out, I'm just going to get x to the 4th, right? And x times x squared times another x. And so this is a positive leading term with an even degree, which means our graph is going to go up on both ends. So for our end behaviors, we can say our limit as x approaches negative infinity for h of x is infinity. And our limit as x approaches infinity for h of x is also infinity. So as we're moving out towards negative infinity to the left or infinity to the right, we're going up towards positive infinity. Our y-intercept, we just still want to set x equal to 0, like we learned way back when. And so we want to find h of 0 here. We can use some color. So this is going to give us a 0 plus 1 times a 0 minus 2 squared times a 0 minus 4, which is going to give us a 1 times negative 2 squared times negative 4, or a negative 16. Right? We get a negative 2 squared is 4, and 4 times negative 4 gives us that negative 16. So I can go maybe my negative 4s on my y-axis, negative 4, negative 8, negative 12, negative 16, and keep that on the graph. Now I want to do what we were just practicing, determine the x-intercepts of the function, their multiplicities, and how the graph will behave near the zeros. So we'll see it so we can keep it so we can see the whole function. Our zeros, multiplicities, and behaviors. Our zeros are at negative 1, 2, and 4. With multiplicities of 1, 2, and 1, respectively, which means our graph is going to cross, touch, and cross. So we can go by 1s on the x-axis to make that easy to see. Negative 1, 1, 2, 3, 4. We're going to cross at negative 1, 2, and 4, or we have x-intercepts of negative 1, 2, and 4. We know from the end behavior that we're coming in from the top. We don't know if minus 16 is our bottom. You're welcome to turn wherever you want. We learn where that actual turn happens and where that minimum will be in calculus. But for now, we just want to turn because we know we come back to our x-axis at 2. Since we're just touching for that even multiplicity, we're going to bounce off 2 or just touch the x-axis there and stay below. And then again, we don't know where that minimum is, but we do know we have to turn back to go up through our x-axis at 4 for that other x-intercept. So it's going to look like a big W. And that was step 4. We used the degree, end behavior, and multiplicity of the zeros to sketch the graph of the function. So we knew both ends were up, we knew we crossed at negative 1 and 4, and we knew we just touched at 2. All right, for 6, we're going to work the other direction, write an equation for the graph below. So I want to track my zeros and their multiplicities. I've got a 0 at negative 1 with a multiplicity of, we always assume as low as we possibly can. So in this case, multiplicity 2, right? We're just touching the x-axis at negative 1. For our 0 at 3, we're looking at multiplicity 1 because it goes straight through. Same with our 0 at 4. The associated factors for those zeros would be x minus negative 1 or x plus 1. For 3, we'd get x minus 3, and for 4, we have x minus 4. And we also know this goes through our y-intercept of 0, negative 24. So I want to start with f of x. That's what I'm calling it. You could pick whatever letter you want, I guess. But f of x equals some value a, just to say there could be some factor, some GCF we took out. And we're going to find that value with our y-intercept. But an a times x plus 1 squared, right? That multiplicity 2, we make sure we have to touch at negative 1, at x minus 3, and then an x minus 4, right? So we're multiplying all those factors together. That's a factored form of our polynomial. And now to find that value for a, we want to put in the y-intercept. So we know our function or our y value, and we know our value for x. So the only thing we don't know will be a when we substitute those in. So we can do negative 24 equals a times, we get a 0 plus 1 squared times a 0 minus 3 times a 0 minus 4. Or negative 24 equals a times 1 squared times negative 3 times negative 4. It's going to give us a negative 24 equals a positive 12a. And if we divide by 12 there, we get that a is negative 2. The negative is good to find because our end behavior is down for this even degree polynomial. We can see degree 4 from our multiplicities, right? 2, 1, and 1. So 4 is our degree. And so we could maybe make you multiply this out, but for this one, let's just write it in that factored form. F of x would be equal to -2 times x plus 1 quantity squared times x minus 3 times x minus 4. And if it said to write your polynomial in descending order, then we'd have to multiply it all out, so we get that a sub nx to the n term all the way down to that constant a sub 0. All right, and then I think we've got one more here, starting all the way from the beginning. So use the function f of x equals -2x cubed plus 9x squared minus 12x plus 4 to answer the following. We want to determine the degree and end behavior of the function. So we start by identifying that whole leading term again. So our leading term is -2x cubed. That gives us our degree of 3 and our leading coefficient of -2, which is less than 0. So we look like this cubic function that's been reflected. We'll start in the upper left, end in the lower right. We can say for our end behavior, our limit as x approaches -infinity of f of x, our function, is positive infinity. So as we're moving out towards -infinity, we go up to positive infinity. And our limit as x approaches infinity for f of x is going to go down towards -infinity. So out to the right, we go down towards that -infinity. We want to find the y-intercept, which is just f of 0. When it's in descending order, it's really, really easy. All those terms with an x are just going to go to 0. And we're going to be left with just that constant term. So our y-intercept is at 0, 4. To factor the function, we're back to thinking about our rational roots. So our p's over q's here. Our p is 4. Our q is 2, really -2, but the signs don't matter. We're going to get plus or minus everything anyways. For 4, we have factors of 1, 2, and 4. For 2, we have factors of 1 and 2. So our p's over q's are going to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/2. And that's it, because then 2 over 1, or 2 over 2 would give us 1 again, and 4 over 2 would give us 2 again. So these are our options. We want to try some work to factor. Usually start with the easy ones. So let's put down our -2, our 9, our -12, and our 4 for our coefficients. And we'll try 1 for a 0. So bring down -2, multiply and add, multiply and add, multiply and add. Not 0, so we've got to try another. We can try -1 next. So same coefficients, we haven't found a 0 yet. -2, 9, -12, and 4. Bring down that -2, multiply with -1 gives us a 2, adding is 11, minus 23, way too big. But then we get a 23, and 4 and 23 gives us a 27. And it gives us a chance to touch on that intermediate value theorem again. Because we know we have a polynomial function that's nice, smooth, continuous function. To get from a -1 below the x-axis to a positive 27 above the x-axis, we have to cross the x-axis somewhere between there. So it gives us a chance to try our fractional zeros here. I'm going to go with a 1/2 because the -1 was much closer to 0 than the positive 1 was much closer to 0 than the negative. So -2, 9, -12, and 4. Bring down my -2. When I multiply, I get -1. Adding is 8. Multiply is 4. Adding is -8. Multiplying gives me a -4, and then a 0 for my remainder, so this one worked. So remember, so far, this would give me that f of x is equal to an x minus 1/2, right? X minus that 0 is our factor, times a -2x squared plus 8x minus 8. I'm going to take out that GCF of -2 and really put it into the other one, but we'll do that in a sec. So -2 comes out, x minus 1/2 is still there as a factor, and then we'd have an x squared minus 4x plus 4. That quadratic is a perfect square trinomial. Half of that middle term squared gives us the last term, 4. Or you can do your factoring work if you need to on the side, but this is going to be x minus 2 quantity squared. So our x-intercepts we can get from that factored form. We again want our zeros, their multiplicities, and the behavior near each. Our zeros are going to be positive 1/2 and positive 2. The the multiplicities, we have 1 for the x minus 1/2 and 2 for the x minus 2. So a 1 for 1/2 and a 2 for 2, which mean our behavior are to cross at 1/2 and just touch or bounce off at 2. We had this nice negative third degree polynomial, so we start at the top, go to the bottom. If I go by 1s down here, I'm crossing at 1/2 and at 2 with a y-intercept of, oh, what was it, 4. So 1, 2, 3, 4. So we got to start pretty close to the y-axis to make this scale kind of work for us, but we got to come down through our y-intercept at 4, through our x-intercept at 1/2. We turn somewhere to come back to our x-intercept at 2, but we just touch or bounce and end up going down to the right forever. And one final question here for f. Determine where f of x is greater than 0 and where f of x is less than 0. So what we want to keep track of is that f of x is our function or our y value. So it equals 0 on the x-axis. So anywhere above the x-axis, in the sky, let's say, f of x would be greater than 0. And down below, we use purple or something, we'd have f of x less than 0. So our intervals, like we did for like increasing, decreasing, or concavity, are going to be in terms of the x values. So we can say f of x is greater than 0 from -infinity until we get to 1/2. And really that's it, right? That leftmost piece of the function is above the x-axis. We'd have then that f of x is less than 0 from 1/2 to 2. And we can union or comma from 2 to infinity. Right, at 1/2 and at 2 we are equal to 0, so we wouldn't be able to include those. If you did have a function when we do some more of the inequalities where we are including a value, if it said, for instance, greater than or equal to 0, right, let's do that for a sec. If this was greater than or equal to, f of x would be greater than or equal to 0 from -infinity to 1/2, and then also at 2. Right, but we'd have to include those zeros if we had optional equality there. But that's it for the standard, so try some stuff, come with questions.